We continue on Learning Workbook page 150. Let's do one more problem. Jose wants to build a fence for a rectangular garden. He has 120 meters of fencing. All right, in the Learning Workbook, there's a three-dimensional isometric view of this garden that he wants to build. What I've drawn here is a top-down view of the rectangle. We're told that this side of the rectangle is x, and we're asked to express the area, a of x, of the area of the rectangle as a function of x. Okay, so let's see if we can achieve this together. The first thing that you want to recognize is one of the things that makes a rectangle is opposing lengths have the same measure. So if this is x, then this will also be x. Now, we need to come up with some sort of description for the other length of the sides of our rectangle. So we're just going to use another variable here. We're going to use the variable z. I have a reason for not choosing y, so for now, please just trust me and use the letter z when you're doing problems like this. All right, so the first thing we're going to do is we're going to play a little bit here with some algebra, specifically regarding rectangles. How do you find the perimeter of a rectangle? You add up all of the lengths of the sides. So an x plus a z plus a second x plus a second z. So x plus z plus x plus z. Well, this is the outside edge of the garden. This is where the fence goes. So the perimeter is actually this 120 meters. So x plus z plus x plus z equals 120. Let's combine our like terms. 2x plus 2z equals 120. Now we're going to solve this for z. You'll see why in a moment. We're going to move this term to the other side where it becomes negative. So 2z equals 120, subtract 2x. And then, since we're trying to solve for z here, let's divide everything by 2. So divide by 2, and we get z equals 120 divided by 2 is 60, 2x divided by 2 is just 1x, and the subtraction sign comes down in between them. So what that tells me is, whenever we have a value for x, we can find the value for z just by subtracting. It would be 60 minus whatever x is. Quick and easy example. Let's say x is 10, then that means z would have to be 60 minus 10, which is 50. So the sides of our rectangle would be 10, 50, 10, and 50. And if you add all of that up, you're going to get 120. 50 and 50 is 100, plus 10 more makes 120. Now, of course, this is an algebra problem. We don't get to make up the numbers for x that we want. But what we can do now is to draw our diagram again and show that instead of the letter z, we can now write what it was equal to, which was 60 minus x. So in place of z, now I can write 60 minus x. And in place of this z, similarly, I can write 60 minus x. Okay. The next thing that we're going to do is we're going to play with the area formula for a rectangle. You might remember that for a rectangle, area is equal to length times width. If this is the length, and this is the width, then the area inside is found by multiplying these two things. So for our problem, the area is equal to the length, which is 60 minus x, times the width, which is x. Using the distributive property, we get 60x minus x squared. And replacing area with a. Now, it just so happens that this equation is a function. For each value of x, there will only be one value of a of x. So I can write this as a of x equals, and putting my terms in descending order, I get negative x squared plus 60x. We now have something that was given to us in all other problems of this type, an equation. You might think about all of the other problems we've solved in the applications so far. We had a ball being thrown up into the air. We had a cost function that we were trying to minimize. In both of those problems, they gave us the equation. In this problem, we have to create the equation as the very first step. Then, once we have that, we can do all of the same things that we did in our previous problems. Okay. So let's write our equation down here. A of x equals negative x squared plus 60x. We're going to need that as we now move on to parts B and C of this problem. Okay, here we go. Part B says, what side length x gives the maximum area that the garden can have. I'm just going to write area and stop the question there. And part C says, what is the maximum area? Okay, let's see if we can figure out how to solve this problem. So let's follow some advice that I gave you in a previous video. Whenever you are reading a problem like this, a word problem, and you can find an extreme word in it, like smallest, largest, biggest, minimum, maximum, then you want to verify that your equation is quadratic and then use the vertex. Well, I see the word maximum in both of these questions. So if I can just verify that this is quadratic, then the vertex will help me answer the question. So, is this quadratic? The answer is yes. If I write the standard form for a quadratic equation, it would look like this. And when I compare it to the equation that we have, we find that the value of A is -1, the value of B is 60, and the value of C is 0. Our equation is quadratic. So, it's quadratic. I have an extreme word value like minimum or maximum, in this case maximum. So the vertex is going to help me answer my question. So x for the vertex is equal to opposite b over 2a. We learned a moment ago that a equals -1 and b equals 60. Let's show that. A equals -1 and b equals positive 60. So plugging that into our formula, we get opposite 60 over 2 times -1. -60 over -2, which is 30. Okay, so our vertex x is 30. Let's write that here. But 30 comma what? Well, to find that, we have to plug into our equation. So, a of x is equal to -x squared plus 60x. Replacing each x with 30, we get a of 30 is equal to -30 in parentheses squared plus 60 times 30. This is 30 squared, which is 900. Then make it negative. Order of operations says do the exponent first. Plus 1800 equals 900. So the y-coordinate of our vertex is 900. Okay, we are now ready to answer both questions from parts B and C of this problem. We just have to be thoughtful about what our variables represent. Remember, this is an x and this is a y. But another word for y is f of x, or in this case, because it represents area, a of x. We know that in this problem, x represents side length, so length. And we know in this problem that a represents area, so a of x is area. Okay, we're now going to answer both of these questions. What side length x gives the maximum area? X is 30. 30 meters. What is the maximum area? 900. Is it 900 meters? No, it's 900 square meters. Okay, we've now finished this problem. However, before we move on to the next one, I want to say one more thing. Remember the answers that we got here. X equals 30. And a equals 900. If you take a rectangle and you make sure that all of the sides of the rectangle fit the equation for this problem, you're going to find something very interesting. Let's go back to our original diagram. This was x, this was x. We found that this was 60 minus x, and this was 60 minus x. We now know what x is. X is 30. So that means this is 30, and this is 30. X is 30. X is 30. This length can be found by subtracting. 60 minus x. Well, if x is 30, then this is 60 minus 30, which is 30. So, what do you call a rectangle that has 4 sides of equal length? A square. The type of rectangle that creates the maximum area inside will be a square. And if you multiply 30 times 30, you get the area inside, which is 900 meters squared.